We start with the first session in the afternoon. So there are two talks, and the first one is by Agissilaos Athanassoulis.
Thank you very much. It's a great pleasure to be here. Thanks to the organizers. Congratulations to Professor Break. Okay, so I'm going to talk about the onset of modulation instability for realistic C states. I'll explain what Alber equation is in the process. So let me set the stage a little bit. If we go to Google Scholar and look for papers that mention modulation instability and rogue waves, you get about 4,000 papers. Now, what I have in mind is a real-life oceanic rogue waves. And you find a lot of papers talking about this. Some papers are saying, modulation instability explains rogue waves. Some papers are saying rogue waves have nothing to do with modulation instability. Some papers are asking, under what condition does modulation instability have something to do with rogue waves? So this is the context where I'm coming from. So it's not so much trying to do, ideal hydrodynamics, trying to understand exactly a nonlinear phenomenon in a phase-resolved way, right? It's more a marine safety point of view. It's more you have a noisy wave field, you have a stochastic wave field, a very high dimensional wave field. You are no longer trying to understand necessarily every peak and trough. You're trying to understand, is there some instability happening there or not? And so the premise for this talk is that the word modulation instability is being used in two senses. One is a neat mathematical sense of linear stability analysis of plane wave solutions for focusing cubic NLS. That's precise, that's well defined, we can understand it. And the other is a speculative or mythological sense where we're trying to figure out, is there something like that in a different context, not in a plane wave, but so the message of this talk is that there is a methodology to work out the most natural possible generalization of modulation instability to realistic states in a systematic, well-defined, quantitative way, just as quantitative as when we talk about for plane waves. Okay, so this is called Alber equation. It's an approach, it's not an equation really, it's a methodology. Irving Alber was an American researcher who was visiting the UK in the 70s. His background was transonic turbulent boundary layers. He worked with Keith Stewardson at some point and came up with this 1978 paper where he would try to understand what the modulation stability looks like for a wave function that has a power spectrum, is not a plane. So this is a reasonably well-known paper. It's not like a completely obscure paper, and a lot of people have tried to work on it and push it further, but certainly it's not very widely used. It's not as widely used as it could have been. And the key reason for that is that there were many outstanding mathematical difficulties in this program. So I've been working on this problem since 2017 with a group of fantastic researchers. Irini Giza and Maria Ptastic are mathematicians. Maria is in the room here. Agissilaos Athanassoulis and Themis Sapsis are academic engineers. Odin Gramstad is an industrial engineer in the DNV. So the DNV is the biggest insurance company for ships. So the engineers bring in the practical questions that help very much guide the theory and try to gear us towards answering those questions. Now, from what I'm going to say about today, the mathematics is mostly in this 2020 paper in kinetic and related models. That's for the precise statements and proofs and everything. In terms of rigorous stuff, but there are other aspects, numerics, interpretation, so on, in all the other papers. Okay, so now we have set the stage. Let me just define my terms very clearly, make sure there's completeness in what I'm talking about. So, okay, the sea surface elevation obviously is a real valid function of space and time. We can represent it through a complex 5D envelope, and as very well known, this envelope satisfies to leading order a focusing cubic nonlinear Schrödinger equation, which is inherently weakly nonlinear, meaning that this coefficient is small and this coefficient is large. So even if it is weakly nonlinear, though, you still have an NLS appearing in ocean waves. Okay, fluid dynamics people know it, ocean engineers know it. And this has some baggage, so you can start asking about solitons, modulation stability, and so on. And modulation instability, again, for completeness, if I take the simplest plane wave solution, so that is a constant in space, it's a function of time only, it oscillates in time uniformly in space. If you take that function up there, you plug it in, it's automatically a solution by construction, and then you ask, is it a stable solution? So if I take that plane wave and I add a localized inhomogeneity, what does the inhomogeneity do as time passes? So you can plug it in, you can derive a nonlinear equation for the inhomogeneity. You can say, well, if the inhomogeneity is small, let's linearize. Now I have a linear equation for the inhomogeneity, and I can solve by Fourier transform, and I get modes of the solution. So the mode with wave number zeta is a solution with frequency omega of zeta, when omega is satisfying this relationship. Now, what does this say? This is a focusing equation, means P and Q have the same sign. So this is positive Q over P. So here you have a positive number. So if zeta is close enough to 0, your omega square is negative, means your omega is imaginary, means you're going to have exponential growth. So, okay, that's a very well-known linear stability of plane wave solutions for NLS. Okay, now so this is on the one hand, we have NLS and modulation stability. We have to appreciate a little bit, you can call it data science, you can call it initialization. So this is as a deterministic problem. If we're trying to solve our nonlinear equation, what we find depends very much on what initial condition we put. So we need to ask at some point, what does a typical realistic C-state look like? And the ocean engineers will tell us, well, that's easy. We know what it looks like. It looks like a typical realization of a stationary homogeneous random process characterized by a known power spectrum. By this, of course, they mean stationary homogeneous in appropriate time and length scales. So if you are in a point in the North Atlantic and you take second moments, if you go 4 miles to the east, 20 minutes later, you take second moments again, you are going to find basically the same. Of course, if you go to the other end of the world, or if you go 2 days later, you are not going to find the same. So this is a very widely used assumption that in a time scale of several wave periods and in a length scale of several wavelengths, a lot of wavelengths, sometimes you do have this stationary homogeneity, so you can characterize things in terms of their power spectrum. And so a key point here is the vast majority of data we have, especially for the ocean, is power spectrum. Nobody has realistic, position and momentum of fluid particles for a storm in the North Atlantic, as far as I know. So the vast majority of the data we have is here. So if we want to utilize faithfully, we're going to have to use that. And in fact, the marine safety engineers, they go a step further. They say, look, if I have this power spectrum, I can build into it, I can create a realization of that and build into it a correct linear dispersion relation. And then I have a constructive representation of solution of linearized wave equations that conforms to this power spectrum. So maybe we put some stochastic coefficients there, and we put the weights in the wave numbers according to the power spectrum. And now we have a very cheap way to do Monte Carlo, to create hundreds of realizations of these C-states and ask for the probabilities that a sequence of waves with so-and-so features show up. And this they use very heavily. And so a lot of the people who are interfacing with industry will tell you, a lot of the time, you hear this a lot, they'll tell you, 99% of the time, linear theory, meaning this constructive parametrization of the solution for linear problems, of stochastic solutions with linear dynamics, does the job. So the recent, for example, roll stability criteria for the International Maritime Organization, which takes into account the wave climate in different regions, they came out a few years ago. They're using linear theory to come up with the criteria, and then they validate with experiments with CFD, and it works, and it's good. It's not over-engineering, it's pretty much where it should be. So you get a lot of sentiment that, okay, all these nonlinear things are nice, but for these kinds of questions, it doesn't seem like we need them very much. So what's the big deal with nonlinearity? So as we build a theory for modulation stability for realistic C-states, I'm going to go up on their claim. I'm going to say, well, the theory predicts that actually just linear theory should be good more like 99.8% of the time. And we have a theorem now to explain why that happens. But there is a 0.2% where non-linear things happen and they are strong and you need to do something different. Okay, so let's go now to this Alber equation. What's the big deal? We want to do a phase averaged study of our waterways. So let's say we have for our dynamics NLS. In principle, you could have even more richer equations there, but now today it's just NLS. So we want to build a second moment theory. We're going to work on second moments, not on phase resolved, detailed wave functions. Okay, so if I take a second moment of my NLS, the linear part works out no problem. So I start from an envelope U, I go to a two-space autocorrelation. So alpha, beta are two-space arguments. I have one time still. So the new function, the new unknown function rho R has a two-space arguments, one-time argument. So now the linear part works out fine. I get some operators acting on R. But of course, the non-linear term is going to give me trouble. Now I have fourth order moments. I don't have a closed equation due to the non-linear term. So the idea of Alber here, why this approach has his name, is he said, okay, what are the assumptions that we use all the time in linear theory? That the C state is a Gaussian, mean zero, circularly symmetric random process. If I make those assumptions, so if I linearize the probability structure, if I have those assumptions, such processes do have a complex release type theorem. So the fourth order moments can be expressed in terms of second order moments. So if I do this Gaussian closure, I get a closed equation for the second moment. This is under Gaussian closure, right? I'm not saying it's exact. So under Gaussian closure, you get a closed second moment equation, and then you also use the observation that to leading order, it's stationary and homogeneous. So the autocorrelation to leading order is going to be just a difference of the lag between the two space arguments. And to higher order, you can have an inhomogeneity. And if you plug this, if you substitute this for the autocorrelation R, you get an initial value problem for the inhomogeneous part of the autocorrelation rho. And this is called the Alber equation down there. So let me discuss it a little bit. This here looks like a funny Schrödinger equation. This here is the autocorrelation. So this is data. So the first remarkable thing here is we have a place in our equation where data from the field comes in. We finally take into account data from the field. And you have again here your rho. Now you have these strange terms. These are non-standard. So this is rho of alpha beta t everywhere. I'm not writing the arguments just to fit everything in a line, right? But it's rho of alpha beta t, rho of alpha beta t, rho of alpha beta t. But here you have something else. Here you have rho of alpha alpha t and rho of beta beta t. So what happens is the diagonal plays an important role. It deserves a name of its own. So I'm calling this position density. And the diagonal introduces a non-local character in this equation. So this is a PDE, but it has this non-local character up there that is going to be with us and is going to be a very important part of the structure of this equation. Okay, so what are we trying to do with this? Let me summarize what this equation is for and what are the challenges there very briefly here. So we're not necessarily trying to predict the full details of the evolution. The point of this equation is the inhomogeneous part rho growing or not? If it is growing, start with something nearly homogeneous, and then it becomes inhomogeneous. So something else, something's going to give. This is not what linear theory predicts. So if you have made assumptions of linear theory and find nonlinear behavior, it means something else is going on. This is what we would describe as instability. On the other hand, if you can prove that the inhomogeneous part is not growing, then if I start in the linear regime, this approach tells me that I stay in the linear regime. So this is really a consistency condition for the linear theory. If I can prove stability, if I can start from this and prove that rho is not growing, then it's reasonable to say that if I start in a linear regime, I stay in a linear regime. So that's the point of this equation. And this is what's really fortunate here. What Albert showed formally was that the stability condition of whether rho grows or not does not depend on the initial inhomogeneity. It only depends on the autocorrelation or equivalently the power spectrum. So, which is something that you can measure in contrast to the initial inhomogeneity, right, which you don't have in general. So, if I go through these bullets here, there was no theory at all for this equation. Well poses a regularity we first did in 2020. So now all these Taylor expansions and numerical approximations of that are justified. We need to use some new tricks also to do that. Alber derived the instability condition. So what he derived was a sufficient condition for instability of all initial inhomogeneities in 1978. But there was no constructive way to resolve this condition. So if I have a spectrum, is it stable or not? That was one of the main problems and why people, in applications in industry. So in 2017, Odin Gramstedt was trying simply to resolve the stability condition. If I have this spectrum, is it stable or not according to Alber? So we came up with a constructive algorithm that's reliable and quick to check the stability condition for a given spectrum. We proved positively for the first time that when the instability condition doesn't hold, in fact, you can guarantee that the inhomogeneity is not growing, that you do have stability. And I call this Landau damping because the techniques we used are very much parallel to what people do in plasma physics, where this term comes from. Of course, this is a natural generalization of classical modulation stability, because if your spectrum goes to a delta, then you recover the classical modulation stability as you would expect. And in contrast to the classical modulation stability, the main finding here, if I can say, to 1 degree of freedom, is that if your spectrum becomes very narrow, you're becoming unstable. If your spectrum becomes very broad, you are becoming stable. So there is a bifurcation. There is an onset of modulation stability, which has no counterpart in the classical modulation stability. Okay, so here I see I'm going a bit slow on time, so maybe I don't spend too much time on the technical stuff. Let me say it makes sense. So here you have a two-space formulation. Your two variables are space. You take one Fourier transform, you can go to one space, one momentum, like a kinetic equation. If you take two Fourier transforms, you can go to two wave number equations. So these are all equivalent formulations, let's say in different frame of reference. So if you take some Fourier transforms, and let me show the main idea. This is formal. It doesn't work like that in the proof, but this gives the idea heuristically. So you have your linearized equation up there. So first term time derivative, second term controls essentially the group velocity of the inhomogeneity just traveling on its own. The third term controls the interaction of the background spectrum with the inhomogeneity. And the interaction happens through the position density, technically the inverse Fourier transform of the position density, but I just call it position density, which in this formulation shows up as a marginal distribution. You integrate in one of the wave number variables. So F up there, again, controls the homogeneous part of the second moment. N is the position density, is a marginal of F. And you want to see what is the effect of the third term, what's the effect of the interaction of the homogeneity with the background. So heuristically, you would write this in mild form. And when you go here, you observe that now if I integrate in the K variable, I can get a closed problem for the position density. So I have the position density minus the free space position density. So what the position density would have been if there was no background spectrum, which we know explicitly, is equal to a convolution in time of the position density itself. So you get a Volterra integral equation for the position density with a known kernel there. Formally, you solve by Laplace transform, and that's the solution. So now you have a derivation of a stability condition. Obviously, if your transfer function doesn't have poles on the right half plane, you expect stability. And so that's called the Penrose type stability condition. It's something similar shows up in plasmas. So this is Alber's, as he called it, eigenvalue relation, which is sufficient condition for instability. And you see that they're essentially the same thing. This is better at handling limiting cases, let's say. It's a bit regularized, but fundamentally they're the same thing. And the only thing further that I want to note here is that this kernel H tilde is a Hilbert transform and contains the power spectrum inside it. Just as information, I'm just throwing it out there. So what's the theorem? The theorem says if you have a spectrum that satisfies a stability condition, then the solution of the linearized equation, you have Landau damping, which means the derivative of the position density has finite space-time L2 norm. So as you integrate over all of space and all of time, the L2 norm of this is finite, which means the derivative of the position density has to disappear in time, right? It has to die in time in order to have this integrability. So you're not saying the inhomogeneity goes to zero, you're saying the inhomogeneity goes to something flat. So it goes something homogeneous, right? So there are no concentrations of interesting things happening. You do really have just everything disperses out. You have this flat picture. And in fact, you can do a bit more. You can build a wave operator. And thus you can justify. So when this happens, basically this term doesn't do anything. So the existence of the spectrum, the interaction of the inhomogeneity with the spectrum doesn't do anything. The inhomogeneity in the whole field propagates just with the group velocity, macroscopically, let's say. That's all that goes on. So that explains why linear theory is so successful in that sense. Let me discuss very briefly the proof. So you would like, I mean, naively, you invert the Laplace transform. That's all you have to do. So you're going to take a contour to invert. Now, ideally, you would like to take the imaginary axis, but you cannot do that because these guys are Hilbert rotated Hilbert transforms. You have a jump across the imaginary axis. So it's a non-smooth area. So you have to go a little bit to the right. So if you are delta to the right of the imaginary axis, you have a small exponential growth. But let's see, maybe it works out. Can we take the limit delta going to zero? Can I interchange integrals and limits? The problem again here is, so these limits in here, delta going to zero, because they're Hilbert transforms, you have Sochotsky-Plemeli limits, you can compute the limit, but it has slow decay in S, and at face value, it's not L1 in S. So you cannot exchange limit and integral. And that's why usually it's not done like that. So what we did here, we used a different frame of reference and some very technical analysis of H tilde and some novel decay estimates actually for an F. And you can just barely show that because of the special structure of everything, this happens to be L1, and you can use dominated convergence and exchange the limit and the integral, so without any details. And we are very happy and talking to our industrial friends, so proud of ourselves. And they said, yeah, that's great. That's fine. I have a spectrum. Is it stable or not? This is what I care about. So let's talk very briefly about that. So if we use Alber's formulation, which is maybe simpler, so you have this very nonlinear function of a real number x and a complex number omega, and you're saying, is there an omega in the right half plane so that this is equal to 1? So let's freeze the x. Let's say we work it out for 1x at a time. That's not the big problem. So is there an omega so that this is equal to 1? An omega on the right half plane. So the way we deal with this, we say, if there is such an omega in the right half plane, I can take a big enough D figure to contain it. By D figure, I mean a semicircle where I have excluded the strip close to the imaginary axis, right? So as I take my parameter R to be larger, so the semicircle is larger, the distance from imaginary axis smaller. So if omega is anywhere on the right half plane, for a large enough R, I'm going to include it. So let's say it exists, let's say I include it. Now I'm going to apply the argument principle. I'm going to say that if I apply an analytic function on this complex plane, and I go to the images under that analytic function, this contour that winds around this point, the image of the contour will wind around the image of the point. And the point here is, why is this helping me? Because I don't know where omega is, but I know h of omega. H of omega is a real number, is 1. I mean, depending on your normalization, it could be another real number, but h of omega is known, is a real number that is known. And this is a known contour, so I can go and apply H tilde to this contour, and I can ask, is my contour winding around this known real number or not? And this tells me if I have a stable spectrum or not. And then you have to try for different wave numbers x. I showed this is, you have to do it once per wave number. So in an unstable spectrum, you would get these lines like this in the complex plane. And if the spectrum is unstable, it means there exist some wave numbers for which the lines do wind around this target point. And of course, as you take larger and larger x, the lines shrink to 0, nothing interesting happens because it's a baseband instability, it is modulation stability. While if you take a stable spectrum, no matter what x you take, the lines never reach out and wind around the point. So that's how you check stability of a spectrum. So let me just go over this slide a bit. So we went on and applied this to the North Atlantic scatter diagram. So this is a big data set, reference data set from the DNV. They have measured 100,000 sea states in the North Atlantic, and they have fit parametrically each of them to an alpha gamma. So alpha gamma, sorry, let me go back. This is a parametric spectrum for ocean waves called the zone swap spectrum. So alpha is just a prefactor, gives you more power. If alpha is large, you have more power. Gamma is a peakedness parameter. So alpha is more power, gamma is narrow, is more peaked spectrum. Larger gamma, more peaked spectrum, smaller gamma, less peaked spectrum. And what they did is they took all these measured sea states and they fit them. They know how, they have some recipe to do that. And they give you points on the alpha gamma plane. So each blue star is a measured sea state on the alpha gamma plane. And with it is associated a likelihood of, if you take a random point in the North Atlantic at a random time of the year, what's the likelihood that you land on this sea state? So you see this pattern there is like a straight line. So more power, either they have a cutoff, gamma has to be between 1 and 5 in what they do. So more power, you would have larger gamma. The more interesting, the more severe sea states would also be more peaked, the power spectra. And so people were they were thinking the alpha gamma plane, there must be a separatrix between stable and unstable spectra. And it's visible, there is a red dust line here, a blue dust line here. So this existed in the literature shortly before we came in this problem. People were trying to do it, but they were saying, we don't know if this is correct. We're guessing this has to be somewhere there. And the black line here is what we did with this method that I just described. So the finding here is the vast majority of realistic sea states are on the stable region, are below. So you have Landau W, you expect linear theory to do well. However, you have these superstorms up there with gamma equals 5 that are unstable. So you do get plausible sea states that the most extreme sea states that you can imagine are unstable. Now, these are really rare, really extreme. They have a combined likelihood of 0.2%. So there, different things happen. Linear theory doesn't apply. And thank you. And the question becomes then, can we understand what does it mean to be an unstable spectrum? What does it mean to have to cross this separatrix and have this bifurcation? So this is really a very fresh question. And we're thinking about it. There's a lot to be understood there. Okay, one thing that we want to emphasize here is in a lot of the literature, there is this tendency to say, oh, we have lots of extremes, we have modulation stability. We shouldn't think that all extreme events are due to modulation stability. There are other nonlinear mechanisms, there are linear caustics. So here now, by modulation instability, you have something very precise in mind. I start with a homogeneous looking solution that is a realization of the power spectrum, and I add to it a localized inhomogeneity that does not come from the power spectrum, that is much smaller than the background solution, and I'm asking, does this inhomogeneity grow or not? If the inhomogeneity grows, then I'm going to say this is modulation instability. So I'm not just going to measure extremes overall and claim that this counts modulation stability. So what I'm doing, I'm creating an initial condition that is the best of our ability, a realization of the power spectrum. That's the background solution, that's the baseline. And then I take that initial condition and I add to it a localized perturbation that's localized in a region much smaller, that is very non-homogeneous, let's say. So it really should stand out. So if this, and then I take I propagate in time under NLS and take the difference, right? And the difference is the inhomogeneity delta. So on the very stable end of the sea states, I expect to find, and I do find something like this. So the high LP norms drop because it disperses, right? So in L infinity it drops, in L4 it drops, and in L2 it stays. So you have a unitary L2 propagation that simply disperses and becomes flatter. This is essentially as if the nonlinearity doesn't exist. This is what free space Renninger would do. And on the other end of the spectrum, you have exemplary modulation instability. The inhomogeneity in this sense grows exponentially for an order 1 time scale, and then it kind of stays there. And we can discuss what it does, and we can discuss what happens as you cross from here to here. You can discuss all sorts of interesting and subtle things. Okay, so sorry, I'm just plotting this. Okay, this is how it looks if you take these points the red points here. So this is the most stable one, this is the most unstable one, and I'm measuring the maximum amplification of the homogeneity delta. I start with about 1% homogeneity. So here you have an order 1 event. Here you have a rogue wave, basically. So over here you have something that is twice or 3 times as large as the background solution. And let's discuss what happens. Let's try to understand it better. And here is where our ocean engineer friends always cut us off and say that's too neat. That's too neat. People have looked at things like that. Nobody ever saw this. Nobody has a pixel like this. Why does nobody have a pixel like this? Now, a big part of the answer is I'm not claiming that extremes switch on suddenly like this. There are linear extremes. This is modulation stability. But still, if a nonlinear instability switches on like this, why has practically nobody seen that? Why has nobody reported that? So now we're working on this, and I have an answer. And the answer is that you need potentially hundreds of wavelengths for this to happen. And we did have to use hundreds of wavelengths for this to happen. And people are not using hundreds of wavelengths. So basically, phased resolve simulations in terms of extreme events and things like that systematically suppress modulation stability. That's a preliminary, that's a tentative, that's a conjecture, let's say. And I'm going to show you why I claim that this is the case. So if we think of classical modulation stability, to make it very simple, let's say now instead of doing it on the infinite line, let's do it on an interval of length L with periodic boundary conditions. Let's periodize the problem on a length L. Every step follows through the same, except instead of zeta, continuous wave numbers, your solution has discrete wave numbers, 2 pi n over L. So the mode n equals 0, nothing grows because this is just constant. N equals 1 is the smallest non-zero wave number. For n equals 1, observe that this is a fixed number. This is a fixed number for n equals 1, right? It could be that this is positive and there is no instability. In fact, the length has to be large enough so that you have even one unstable mode. So if you do it in terms of P and Q like there, you find what is the shortest length that gives you even one unstable mode. Otherwise, you completely suppress modulation stability. And if you substitute the P and Q so that you get the lambda 0, the wavelength, you get that the domain has to be order lambda 0 square to give you even one unstable mode for the plane wave. Even plane waves are stable when you do them on a short enough, are linearly stable. There is no modulation stability on a short enough interval. So if you have lambda 0, 300 meters, 500 meters, 700 meters, this is a lot. This is a lot. So what we're doing now, just like you can do the classical modulation stability on an interval, you can redo the Alber equation on an interval and find a clear prediction for the length scale required in order to see the modulation stability. So the message here is, I think phase resolve simulations for extremes systematically suppress generalized modulation stability, and that's why you have these people saying that there is no modulation stability, everything is linear. Yes, everything is linear in the numerics because we're taking 2 short domains. That's my conjecture at the moment, and we're working on it, and more things are on the way, more precise things, both on the theory side and on the numerical side. Okay, so a very quick summary. I hope I'm okay with time. By Alber equation, I mean a methodology to do moment equations on NLS. It predicts the existence of a stable and an unstable regime of stable and unstable power spectra. It explains systematically the success of linear theory for certain kinds of problems that otherwise is unreasonable. The onset of this instability is not well understood, and a factor here that makes it worse is that we don't appreciate the kinds of length scales that we need to resolve in order for this to manifest. And let me just say that what I showed here, starting from the NLS, in principle, you can redo all of that starting from Zakharov equation. You can be fully broadband, you can be fully 2D. We're working now on a crossing seas problem with Maria, and you can include other, even some models for wave breaking and wind forcing, approximate models. So you can have non-Hamiltonian physics. You can do much more. So this is not a 1D narrowband NLS trick. This is a more broad methodology that you can try on different problems.